what we're going to try to do in this talk, this is Escher's woodcutting called a square limit, which has a lot of fish. And sort of the basis for this talk is this paper by Peter Henderson. It was originally written, there was an original version from 1982. This one is from 2002, which is a revised version, slightly changed to the approach. I haven't been able to get the original, unfortunately. So I've based this talk off of this 2002 version of Peter Henderson's paper. Now what he does in the paper is that he creates a picture algebra to reconstruct this Escher picture using functional programming. And I thought that was pretty cool, so I've tried to do the same thing. Now what he does is that he creates some simple picture transformations and combinators, and he uses those to construct this, which has the same structure as the Escher artwork, which is kind of impressive, I thought. Yeah, so I'm going to try to do the same thing. Now, I'm going to use the programming language Elm, and I'm not an Elm expert, but it's nice because it runs in the browser and it produces an SVG, which is nice for this exercise. What is a bit unusual in Henderson's paper is that the notion of a picture is not like a collection of pixels, rather it's a function from some bounding box to some rendering. That's going to be very useful for us. Let's see if I can find my code. Where's my code? I can't find my code. Oh, here it is. This is my code. Yeah. So what's going on here is I have this, whatever my picture is, and I'm passing a box to it, which produces a rendering, which I then draw in the browser. So for now, what we have is this kind of unimpressive thing, the letter F, which is drawn. And just to sort of to help see what's going on, I can render this sort of, I could have, I thought I could. Let's see, for whatever reason, this isn't running. So I have this Elm thing running in the background, and for whatever reason it died, which is kind of unfortunate. This is kind of strange because this is not correct. And I don't have time for mistakes. Okay. Oh, yeah, no slash, thank you. Oh, here we are. So this is the bounding box. So the bounding box consists of three vectors. There's an A vector pointing to sort of the start of the box, and you have a B vector going out here, and a C vector going up there. And this sort of now determines the shape of this picture. So whatever box I give it, this poor picture sort of has to fit inside that box. So I can change my box. Well, I can move it, that's one thing, but I can also sort of make it more like this. I can tilt it, all by manipulating these vectors that determine the box, right? So let's see, I do something like this. And yeah, so the box sort of has, or the picture rather, needs to fit within the box. So it sort of self-renders within the box that I give it. Which is pretty cool, because then I can use this to make these transformations, right? So if I want to turn, for instance, my picture, I can just turn the box just in time before passing it to my picture. Then it's like I have a turned picture. So that's the first thing I'm going to try to do. Let's see. I'm going to create a function now called turn, and I have these snippets to speed things up. So turn is going to be a picture-to-picture function, and a picture is just a function from a box to a rendering, so something like this. So the idea here is I'm going to just, for my turned picture, I'm just going to create a new picture which I create by calling my original picture with turned box. So sort of by visual thinking here, if I had this turn box function that would just turn the box for me, that's going to produce my turned picture. So turn box. Now what's going on here is I have this box which consists of these 3 vectors, and I just deconstruct it and then I sort of reconstruct it here. Now I reconstruct the exact same box for now, but the idea is that for my transformation, I'm just going to, well, I don't have my original box anymore, but that's fine. What I'm going to do is I'm going to sort of take my original A vector and then add the B vector to it so that I sort of move over to wherever that pointed to. And then for my new B vector, that's going to be the old C vector, which points right up. And then finally, I guess it should show you the vector functions. There's nothing much interesting going on, but with these vectors I can add them, negate them, subtract them, and scale them, and so forth. Yeah. So the final one is just going to be the B vector, but going the other way around. Right. So I want my original position for this, my original box. Right. So this is my original picture. But for the turned picture now, so I'm going to turn the picture and then pass a box to it. And just to see what's going on, I'm going to render also the turned box, so you can see that it sort of follows along. Right, like that. And you can, sort of an interesting property of these picture-to-picture functions that we're going to create is that they self-compose, right? So you can compose it with itself multiple times. And in fact, well, let's try to do what I just said. So I can self-compose like this, which is going to turn twice, and turn the box twice, like so. And we're going to do that quite a lot, so I'm going to create a helper function, which basically self-composes n times, right? Now, if n is 0, I'm just going to return the identity function. Otherwise, I'm going to return composing the function with calling myself recursively with n minus 1. And you can see if we have an n here, which might be 3, then I can turn 3 times over, and I can turn the box also. Well, the point was to use this n, right? So times n turn box of the box. Let's see if that works. Yeah, so now I turn it 3 times, and obviously if I turn it 4 times, then we're back where we started. Okay, so yeah. Time passes quickly. Let's speed up. Right, the next thing I'm going to do is I'm going to create another simple transformation called flip. Now, what flip is going to do is take a picture and flip it like this. And I'm going to use the exact same trick. Actually, I forgot one thing for this turn thing. Now, since turn box is a function from box to box, and a picture is a function from a box to a rendering, I can compose this turn box function directly with my picture P, which looks strange, but that's sort of a property of having a picture that's a function from a box to a rendering. So that's going to do the same thing. And I'm going to use the same approach for flip, which is to have, if I have a way of flipping a box, I can just compose it with my original picture. That's going to produce a flipped picture. And again, flip box. Now, how do I flip a box? Well, I navigate to the sum of A and B vectors. I negate the B vector, and I'm done. See, flip box, yeah. I have a flip box. And I can flip back and forth. Now, there's no need to flip more than once because we just end up where we started. Final simple transformation we're going to use is something called, well, in Henderson's paper it's called ROT45. I call it toss because it looks like tossing something lightheartedly up into the air. So toss, again, toss box, composed with the picture. I have 13 of these functions to define, so that's what I'm speeding up. And tossbox is a little more involved, but not a whole lot. I'm going to start at A, and then I'm going to add the result of scaling a vector, which is the sum of the B and C vector. And you might not immediately have a picture in your mind of where we're going to end up with doing these things, but it helps just to show you, I think. Now, what I'm going to do is to make it more clear what's going on with this transformation. I'm going to draw the original box and the tossed box at the same time. And it looks like this, right? So this is the lighthearted tossing up into the air. And of course, we can do this multiple times as well. It's kind of fun. Well, actually, let's use this nice times thing. Right, so I can keep going like that. In fact, I created a simple helper function. It's called gather boxes, which, well, where did I end up? I don't want to close it. Let's see. Let's say I want to toss this multiple times, and I want to draw all the intermediate boxes. I have this gather boxes and toss box with my box. And, well, isn't it called gather boxes, though? Well, I imported the wrong thing. So, this one. Now, hopefully I have it, and yeah, so we can keep going like this, which is kind of neat, I think. Well, okay, so that's the third simple transformation. Now I'm going to try to create larger pictures out of smaller pictures, so by combining things. First thing I'm going to do is define a combinator called above. And in fact, I'm going to start with above ratio, which allocates a proportion. So when I put two pictures on top of each other, I'm going to allocate sort of a proportion to the top one and one to the second one. So the M is the sort of the weight given to the first picture, N is the weight given to the second picture. And then, then defining sort of the fair treatment of above, which gives equal weight to both pictures, is just going to be calling above with equal weights to both pictures. Now, okay, above ratio, well, it's going to have to produce a function from a box to a rendering. And then I'm going to calculate just a fraction allocated to the top picture. So I'm combining, well, dividing by the combined weights, right? And then I'm going to produce a top box and a bottom box by calling a function that I don't have yet called split vertically. That's going to split my box into two boxes. And when I have that, well, what I want to produce is a rendering, and a rendering is just a list of shapes. And that's the sort of the result that I get from now rendering my first picture within the top box and the second picture in the bottom box. So if I just have this split vertically thing, let's see, split. Actually, I think I'm going to start cheating a little bit more because we're running out of time. So split vertically is going to take the top box, move it vertically, be sort of on top of the bottom box, and then scale it appropriately because it needs to shrink, right? I'm going to do the same thing here for move vertically. I'm going to cheat for that as well. I'm sorry. And yeah, I'm going to cheat also for scale vertically. There's nothing much interesting going on here anyway. Moving is just adding a little bit of going up in the Z direction. And, well, scaling is even simpler. It's just scaling it down. Let's see. So now, hopefully, I can draw something like this. Yeah. Well, I didn't draw the box, but it's not important. So this is my box, and now they have sort of evenly spaced for my two pictures. And I have a similar function for beside. And that's even more boring to watch, so I'm just going to do. So it's entirely the same thing, just putting things next to each other. But I do have to sort of produce it somehow. So now instead of splitting vertically, I split horizontally. And that's basically it. And then I can, let's see. Right. For this now, I'm going to use a different figure. I've been using the letter F for now. I also have a stickman called George. And he looks like this. And he can hold hands with himself, which is kind of an interesting property. In fact, if you change it around, he can sort of high-five himself as well. Now, the nice thing with having defined these functions is that now I can sort of leave this low-level vector manipulation stuff more or less behind and just use these functions to create more interesting stuff. So I have something called a quartet. And a quartet is what you get or is a means of combining 4 pictures into a 2x2 grid. And it's like trivial to implement. So now if I have northwestern picture and the northeastern picture, I just put them next to each other. Same thing here, and I put these on top of each other. And that's basically all I need. So if I now have George here, 4 Georges, which is kind of appropriate, like so. And I can, to make it a little bit more interesting, let's see. I'm just going to transform the different Georges a little bit. And we have something like this. And yeah, I think I'm going to drop these boxes now. So we have something like this. But an interesting thing, I think, is that this is still just a picture. There's nothing sort of particular about it. So I can use that in further transformations. Like so. Yeah. Yeah. Which is pretty cool, right? It composes and scales very nicely. Yeah, so when I have a quartet, I also need a Nonet, and I'm going to cheat for that one as well. The Nonet is similar to the quartet. It takes 9 pictures and arranges them in a 3x3 grid. I'm not going to spend time writing it out because I don't have that time. Yeah. So let's do, I'm going to cheat a little bit here. I have some more letters. I have an H and an E and stuff like that. So I can create a Nonet out of 9 letters, which is going to look like this, right? Which is kind of nice. And you can make it even a little bit more interesting if you turn this name thing into a function. And then you can do stuff like this, which is, again, pretty cool, right? Okay, 5 minutes left. I think it's time to start with the fish. So I have a fish. This is the fish. This is Henderson's reproduction of Escher's fish, anyway. I'm going to create sort of a degenerate above-like function called over. I'm going to cheat. Oh, yeah, I have it. So basically, it takes a picture and then renders it takes a box and renders two pictures inside the same box, which is normally a recipe for disaster, but for this particular fish, let's see, it can be quite nice, right? Because it's a cleverly designed fish. Now, to build a square limit, I'm going to need some basic tiles. And in Henderson's paper, those are called the T-tile and the U-tile. So the T-tile, let's take a look at the T-tile. Well, this is not a completed T-tile because this is just a fish, just to see what's going on. In addition to the fish, I need what I call the northern fish. I get by tossing and flipping the original fish. And if I have now fish n and put it on top of the original fish, then I almost have the T-tile. Oh, whoa. Like so. And I also need the eastern fish, which I get by taking the northern fish and turning it 3 times over. But I didn't actually include it, so I need to draw everything on top of each other like this. That's a T-tile. I need the U-tile also. Let's take a look. I'm going to cheat for the U-tile. It's kind of similar to the T-tile. Basically, what you do is replace the fish with 2 more fish, the southern and the western fish. Like so. Now we come to the recursion. So I'm probably going to run a few minutes over. Is that okay? We're getting real close. So, side. Now this is going to be one of, well, the finished square limit is going to be a Nonet. And I'm going to create now a side which is going to be used 4 times in that Nonet. We already have, actually the U-tile is going to be the centerpiece of the square limit. You can see sort of the same thing, right? Now I'm going to produce the side. Now, base case, very simple, is going to be a blank picture, a function that takes a box and produces nothing inside it. But for the recursive case, I'm going to call side recursively, and I'm going to need a T-tile for a fish, and then I'm going to produce a quartet, which is this 2x2 grid. And that's going to look like this. So I'm going to take 2 copies of the recursive case, and then I'm going to take the turn, the T-tile, and a T-tile. Let's see what it looks like. So, in fact, I had this thing that I imported earlier by mistake, which is this one. And I'm going to also change my visualization just a little bit so you can see what's going on with the recursion, because that's kind of important. So, side. Okay, where are we? Well, this is boring because that's the sort of the degenerate 0th case, right? I just rendered the box. I was supposed to render this side boxes to see what's going on inside the recursion. Right? So this is case 1. This is my quartet. Now this is the blank and the blank, which are the recursive cases. But it quickly gets more interesting when you sort of grow it like that, because it sort of grows towards the edge like that. Similarly, for corner, which is going to be the 4 remaining things that we lack. And I think I'm going to cheat for corner as well. It has the same structure as side. So in the degenerate case, it's going to be blank, and then you have 2 recursive cases, 1 for corner and 1 for side. But that's also another one of these quartets. So let's try corner now. Yeah. Well, I don't have time to go step through it because we need to paint the square limit now. Was it clear though? Yeah, it's okay. Let's try square limit. Another cheat, I'm afraid. Square limit is sort of surprisingly boring once you have these sides and corners in place, because it's basically just a U-tile for the centerpiece, then it's a corner piece in 4 variations turned, and the side piece in 4 variations, and then you just compose it in a Nonet. So it's sort of trivial, almost disappointing. So let's do something like this. Yeah. So I know we're out of time. I just want to show you one more thing. You see, I have what we had here was sort of a faithful reproduction of Henderson's reproduction of Escher's artwork. Now you notice in this artwork that it has colors, right? So I have a variation, if I could just find it. Yeah. This is in color, and it should be running over here, which has sort of this colored fish. And the thing with the colored fish is that you can change its color like this. So it follows the same idea that you can sort of manipulate, not the picture as such, but you can manipulate how it's rendered. And with that in place, you can do a square limit like this, which is, well, so thanks a lot. Sorry for rushing through things. There is I created a workshop for doing this in Elm, so it's called Escher Workshop. I can share the links later on. I don't think I have Wi-Fi, so yeah. Okay, thank you.